Hi, this is Dave Pellerin. Thanks for joining our session today. I'm joined today by Mark Galbraith of ARM, who will be talking about semiconductor verification, design and engineering, and how to make engineers more productive and happy. I'm also joined by Walker Stempel of AWS, who will be talking more broadly about CAE and design and engineering workloads across industries. So thank you, Mark and Walker, for joining today. Before we start, I wanted to talk about the goals of design and engineering modernization and how cloud is really helping to develop products faster. We see it ourselves within Amazon and our various teams, and we certainly see it in external customers as well, that are really helping their engineers to be more productive, to develop products faster, develop products that have higher quality, and to do this in a way that really helps to optimize productivity of engineering resources, which in many organizations are the most constrained resources in the organization. Sustainability is very important as well, and so rapid development of new products that are manufacturable, high quality, ramp quickly to high yields is very, very important. And again, simulation-driven design is a very important part of modern product design today. And as I touched on a moment ago, talent retention is very, very important in the design and engineering space. Again, engineering resources are constrained. It's very important that we keep engineers and developers of advanced products happy and productive. So with that, I want to turn it first to Walker to talk about what we're seeing across industries in CAE, in high performance computing, in support of these types of workloads. So Walker, please take it away.
Thanks, Dave. In the past 3 years, I've had the opportunity of leading the industry solutions team. And in that time, I've heard from a lot of customers, as have you, around their efforts to modernize digital engineering. And before we start speaking about some of the specifics of those discussions and best practices we've learned from our customers, I wanted to quickly share some interesting data from Gartner that speaks to this. So in 2021, Gartner performs their CEO survey, which captured responses from around 465 business leaders in more than 30 countries across many industries. This survey is conducted annually for more than 10 years. And so they get a broad base of data to compare changing industry trends. And this year's results were pretty interesting. The top of mind items for business leaders have significantly changed. And primarily the reason given for this is the pandemic and how that's forced CEOs to place fresh emphasis in certain areas and not as much emphasis in others. And you can imagine the unprecedented change, driving those priority changes. The top workforce item, or the top item that gained momentum in this year's survey, was the workforce. So 24% of CEOs named that among their top 3 priorities. That is a 24% increase year over year for the same survey. This rapid rise is a sign that CEOs are acknowledging the toll that 2020 took on their people and the role that the skilled talent that they employ play in enabling their organization not just to meet the needs of their customers, but to innovate and drive new experiences and solutions. Among the biggest losers in this survey for this year was cost management, which slipped to 7th place, and as a result was a 17% drop year over year for those same CEOs who had flagged it the year before as a leading priority. So if I were to summarize my own observations over the past 3 years, what we've seen is a rapid adoption of companies to adopt digital technologies. Companies are becoming increasingly global and products are becoming increasingly delivered across geographies, and they're becoming more complex. So product and design leaders are learning now to splice this new digital DNA into their cultures and their processes and the technologies to transform into the top performing organizations they need to be to compete. And this was from the prior year's survey, the same survey where Gartner again surveyed the same CEOs who specifically mentioned that they anticipated their entire industry would be disrupted by the year 2026 as a result of digital modernization. So, while innovation is critical and to adopt digital modernization for digital engineering practices, it turns out it's actually pretty hard. And, I talked about some of the challenges with the organization. So, in the time that we've been working with customers to help them modernize, I've noticed that those companies that have been able to achieve results in digital modernization more quickly for engineering processes have adopted a slightly different mindset over what their peers might have done that had more time and market. So one of the key elements we've noticed is their own perception of their organization. So leaders in R&D are viewing engineering as an innovation center versus the traditional view as a cost center. And if you look at the sort of the level of effort to optimize in the way that R&D IT, as an example, would deliver tools to their business units, in the past, they might spend a whole lot of time focused on infrastructure, RFPs to acquire large data centers and fill those with servers for PLM and ERP and SAP and the rest. And then they would spend some time optimizing those tools. And then finally, with what time was left over, they would spend that with the actual business units to help them get the best use out of that architecture. In complete contrast to that, what we're finding now in discussions with customers is 100% reversal, where they're focusing on the experience of that engineer. And this makes a lot of sense, because if you look at the balance sheet for most companies that are doing discrete manufacturing, it's pretty obvious to see that the the operational expenditure associated with the people, the talented engineers, the designers, and the supporting teams that help them develop new and innovative experiences for customers greatly outweigh any of the costs associated with tools, and certainly the costs associated with infrastructure. So what we find is these customers, these innovators, these leaders in industry are working to get products in market more quickly, analyze feedback from customers such that they can react to those changing market conditions. In that way, they can reduce costs and they can experiment more on new ideas. And the more experimentation, the more quickly they can get ideas to market. And there is a trend or a core Amazonian principle that this quote from Andy Jassy articulates. And that is, to be able to deliver new outcomes, you have to try new things. And that is going to produce some of those experiments will be failures. And so these leaders in digital engineering modernization are hyper-focused on mitigating the collateral damage associated with the failed experiments, but also enabling the innovative spirit and the builder spirit within their own engineering and design community, so they can optimize productivity. So again, calling back to some of the best practices of public cloud, there's some parallels to what's occurring within research and development organizations that match very closely to some of the thought leadership that came from cloud native application development. And so one of those examples is this notion of monolithic applications. So, one large architecture that gets deployed that has a great deal of dependencies on many teams. It does a lot of things. There's only a few people who understand how it works, and it probably gets updated on the order of any 5 to 10 years as you implement new technologies, because there's dependencies on roadmaps and other items that you don't have control over. So if we looked at in contrast to a more modern approach for application development, there's a notion of microservices, which are small encapsulated functions that are loosely coupled, that don't have dependency on each other, that can be updated in real time. And so upfront development, engineers have to coordinate their changes and make sure that they're not making any changes that will break something in the monolithic architecture. When you move to a more microservices delivery, leveraging things like CI/CD and delivery pipelines for that software, you don't need to rebuild the entire application to deliver new capability for your engineering and design users. You can iterate over that quickly and treat that more as a continuous change element versus a static upgrade over time. So as we see customers move through the phases of their modernization of engineering workloads, starting with the monoliths and moving to a more microservices delivery approach, this parallels, as I mentioned, some of the ways that customers in other industries and in other areas have adopted public cloud. And so we see a pretty clear path. And in the context of AWS, we use this paradigm known as the Cloud Adoption Framework. And it really starts with rehosting, which is a lifting and shifting of existing processes. This is critical for engineers and designers because learning new tools and processes is going to have an initial hit to their productivity. So you want to mitigate any sort of challenge for them early on as they move into a more agile delivery mode. And you do this just by taking the existing tooling and landing it in a public cloud. Now you get some benefits for this in terms of security and scaling, of which Mark mentioned, and you'll hear more from Dave about. But there's this really we view as step one. Then we see customers moving into the replatforming phase, which is they start to decouple those monoliths, break off pieces of that to improve the ability to deliver new capabilities in an agile way, but also to improve security and scalability for some of those underlying applications. Finally, we find customers start moving into the refactor and reinvent phase. And this is where things get really interesting. I'll talk more about it in a second, the way that we've been able to leverage AWS Managed Services. But this entire journey comes from a commitment to remove any undifferentiated heavy lift associated with supporting research and development teams. So this really is based on a foundation of automation. So what does it mean in the context of the Cloud Adoption Framework, and how does that apply to modernization of engineering and design workloads? Well, again, another thing that we've seen over the past 3 years is that not every customer is trying to solve the same scale of problem. And that's defined on the bottom axis of this conceptual chart that shows scope of vision. And equally, not every customer has the same level of appetite to invest in modernization of their digital engineering workflows. And more broadly, when we say things like invest, it isn't necessarily just monetary investments. This could be investments of time, or more importantly, of those talented engineers and designers, the operations teams that support them. So as we see customers move from that rehost phase that I mentioned up through the re-architecture phase, we see that can be accelerated through a greater investment in their capability to deliver agile outcomes. That might be investing in their own staff to staff up DevOps capability, or it might be partnering with one of AWS partners to rapidly move them into a state like maybe they're going from rehost, now they're in replatform by working with one of our partners. So where does AWS fit into this migration? AWS, of course, offers greater than 200 services, many of them being announced this year at reInvent, are 100% applicable to modernizing the engineering and design workloads. And I haven't mentioned those yet, but primarily we're focused with helping customers migrate electronic design automation workloads, some of the design verification, which we're going to hear about later from Mark, the CAD workloads or engineering desktops. So those are the more interactive engineering applications that are being used for things like pre and post processing. The CAE workloads, which can encapsulate physical simulations like electromagnetics, thermal simulations, computational fluid dynamics. And then today, the single source of truth for engineering data at most of our customers is the PLM. So re-hosting the PLM within AWS Construct to improve scalability and security. So all of these discrete workloads stitched together enable a full engineering and design workflow. And the operation of these today in the context of an on-prem data center is wrought with silos and struggle to keep those individual systems running and communicating with each other. A major benefit from customers who've optimized and modernized engineering on AWS is taking advantage of that automation, which decreases the heavy lift on the operational teams and allows them to implement services much more quickly. And those, as I mentioned in this box, are some services, managed services from AWS, like CloudFormation, and then our pipeline, our CI/CD pipeline services like AWS Code Build and Code Commit. The really exciting thing is when we see customers complete the rehost and replatform of these workloads, then they start taking advantage of higher order AWS services. So Dave mentioned that earlier. These are things like Amazon SageMaker to apply machine learning to some existing engineering workflow, leverage machine vision and serverless technologies to even develop their own cloud-native applications specific for engineering and design. So I'm sharing here on this slide, and this is a reference architecture for one of those blueprints or patterns in which AWS can help rehost an existing workflow today and take that in contemplating cloud delivery paradigms like pay-as-you-go and cost. So this is a reference implementation for computer-aided engineering. This architecture makes use of best practices in cloud to leverage multiple availability zones. So what that does for us in the context of engineering applications, that might be mitigating things like downtime or disaster recovery in the event of a slowdown in a specific availability zone or a region. In the context of CAE, these simulations are massively computationally intensive. So being able to access and tap in to the depth and breadth of the AWS compute portfolio means reaching across data centers. And so that's what one of the functions enabled through multiple availability zones. So we move the job to where the compute capacity is, or the storage, or networking, or GPUs, or whatever it is. The compute breadth, of course, is a game changer. As Mark and Dave will mention, this is right-sizing the job to meet the need, as opposed to deploying heterogeneous resources that might be underutilized or worse, overutilized, increasing time for engineers to get new products in market. Operational best practices in security are, of course, the things that are driving some of the best practices in cloud. And here I just share an example from an internal customer, of which you'll hear Dave talk about in a moment, which is Amazon Devices, that is able to achieve multidisciplinary optimization in a way they never were by leveraging public cloud, specifically AWS, in this reference implementation. I'll mention briefly, I know we're talking a lot about semiconductor today, but I want to mention another customer, which is Amgen. Amgen was a very interesting use case in that they're a team that was focused, again, on optimizing their most valuable asset, the scientists required to develop life-saving capabilities for customers. And in order to enable those scientists coming from multiple disciplines, they needed an easy-to-use platform to do multi-physics simulations. They needed that to be scalable, core tenet and capability of the cloud. But they also needed the ability to adapt to a cloud delivery mechanism and implement cost and performance monitoring and automation. So being able to leverage a dashboard to be able to see exactly how resources are being consumed in real time. And then this team is also a very powerful example in the fact that Amgen is proud to adopt open source tools and technologies to be able to move rapidly to deliver new experiences for their users. But of course, given that this is a highly sensitive industry, they have to adopt best practices around enterprise guardrails for security and infrastructure guardrails to make sure that their IP stays secure. So after validating the performance of their multi-physics applications on AWS leveraging Amazon Elastic Compute, EC2, Amgen deployed a AWS reference implementation called Scale-Out Computing on AWS. This open source solution provided the platform for that user-friendly interface for the scientists and allowed them to further embrace their strong builder culture and really encourage the expertise and bring up the teams that are looking for alternatives to off-the-shelf solutions. The team is using several dashboards today to monitor cluster utilization. They've implemented budgets across multiple teams, and they continue to iterate and develop against that platform to deliver new experiences for their customers. With that, I want to turn it back over to Dave now, who will actually share a little bit with us on why would you even consider leveraging AWS in the first place.
Well, thank you, Walker. So in summary, why use AWS to develop advanced products? What's the benefit here? Well, clearly, as Walker's described, getting access to extreme scale when needed, running simulations at high scales, getting results back fast. This is something that's possible in cloud that's virtually impossible in traditional engineering resources on-premise. In addition, getting access to the most advanced technologies for compute, for storage, traditional CPUs, non-traditional compute environments like GPUs, FPGAs, access to AI ML to help to optimize those workflows, also a very important part of engineering productivity. And the ability to be flexible, to flex up, flex down, try new experiments, and really innovate more quickly in engineering workloads. This is true for simulations, verifications, use of AI ML and big data for things like yield analysis. There's many reasons, apart from simply having access to scalable engineering compute resources, to run these workloads on cloud. And again, to provide that data-driven innovation that's only possible using cloud. As I mentioned earlier, we experience this ourselves every day at Amazon. We have multiple design teams doing advanced silicon devices, doing products that are in homes. We also have use cases in our robotics area for fulfillment centers. We care deeply about the semiconductor industry and on rapid innovation in high tech and semiconductor, in our own supply chain, in our own operations. And we do use cloud internally within Amazon to accelerate our engineering use cases, to accelerate our product development. And when we think about acceleration of product development, we think about that entire supply chain. Whether we are designing semiconductor devices or sourcing them from external partners, or we are developing next generation server and storage solutions or consumer devices, we have to view that entire supply chain. And when we develop new products, make use of data throughout that supply chain in support of rapid innovation, in support of quickly developing high quality products to delight our own customers. And increasingly, of course, we're seeing external customers do the same, right? Take advantage of cloud, take advantage of data-driven methods and intelligence from that supply chain to build higher quality products. So again, it's not just about simulation. It's not just about migrating existing workloads to cloud. It really is about modernizing and reinventing the complete product development lifecycle using cloud. An important aspect of this is collaboration across the supply chain. And again, this is an experience we have ourselves within Amazon, but every player in the supply chain has a similar challenge, and that is how to collaborate on data effectively, protect your intellectual property in those collaborative environments. And this particular visualization focuses on the semiconductor world, but this is really true across engineering disciplines, from pharmaceutical to mechanical CAD to semiconductor and electronics. The ability to use cloud to create secure collaboration environments, cloud chambers, you might think of them, that allow you to lock down subsets of data, intellectual property cores, or perhaps try a new software patch for a piece of software that you're using, perhaps in the EDA world, or work with your manufacturing partners on a subset of data from that environment to do things like yield analysis or early lifetime failure analysis to develop higher quality products faster. So cloud really does make this collaboration faster and easier. Certainly, the ability to spin up a new design environment in literally minutes and have that secure and locked down to particular individuals, IP ranges, and monitor everything that's being done in there is a very, very important part of securing the semiconductor and electronics supply chain. When we think about CAE, or electronic design automation workloads, there are well-established patterns that have existed for many, many years, decades even, in the industry. The use of job schedulers for scaling up simulations, the use of remote desktop, license managers, shared file systems. Again, these are well understood, well-established patterns across the industry, whether it's electronic design automation or computer-aided engineering at large. The ability to stand up the equivalent of this in cloud is a very powerful enabler for rapid development of next generation products. Again, whether it's a complex EDA workflow or it's a single application running simulations at scale, the ability to create these environments very quickly on cloud is a huge enabler, not only for creating innovation environments for engineers, but allowing those collaborative environments that I described a few moments ago. So think about cloud as a way to quickly create purpose-built, well-optimized environments for specific projects, or as a shared infrastructure if you have the need to share licenses, for example, across different projects or collaborate between different teams. And lastly, think about deploying machine learning and analytics in these environments on cloud, because those tools are available, SageMaker and other tools on AWS that can augment traditional CAE and EDA environments, allowing you to analyze job logs, for example, optimize use of software licenses, optimize your engineering resources using AI/ML. It's a very important augmentation that you can do for EDA and CAE applications in cloud. Well, with that, I want to turn it over to Mark from ARM to talk about their journey to the AWS cloud, or to the ARM cloud, as the case may be. ARM has been deploying electronic design automation workloads on cloud for some time, and has really been a leader in modernizing those applications on cloud and supporting their engineering teams for higher productivity and happier engineers. So, Mark, take it away.
Thanks, Dave. My name's Mark Galbraith. I'm VP of Productivity Engineering for ARM Limited. And today I'm going to talk to you about the journey to the ARM cloud. So I'm going to start off by telling you a little bit about ARM, who we are, what we do. Then I'm going to talk about our IP and SoC design process. Then we're going to move a little bit into using cloud for how we develop our IP, and then also why ARM in the cloud. I'll then talk a little bit about electronic design automation tools and the performance that we see, and then I'm going to talk about 3 case studies that we've got across physical IP design, hardware IP verification, software development, and then I'll give you a summary on our journey to the ARM cloud. So ARM is the world's most pervasive compute platform. Around 70% of the world's population uses ARM processor technology. And so wherever computing happens, we will be there and we will advance it. So ARM's been around for quite a number of years now. We were founded back in 1990 as a joint venture between Acorn Computers, Apple and VLSI Technology. And really from those very early days, ARM was designed into the first mobile phones, which then of course became smartphones. And so power efficiency was really important to us from the very beginning. And nowadays, many different electronic devices are using ARM-based technology, from those client devices through infrastructure, to automotive and IoT. So ARM is a semiconductor IP business. We work with our partners, and what we're essentially doing is we're the R&D outsourcing for semiconductor companies. And as we build our IP, the technology that we develop is used across multiple different applications, and that allows our partners to then focus on flexibility and giving them the freedom to innovate as they use our products. Partnership is really at the heart of ARM. It's all the way through our culture and into our business model. And licensees take advantage from this collaborative approach that we have right across our ecosystem. So I've got a few data points I want to share with you today. So today, around 2,000 ARM licenses, growing by over 100 every year. And that's across around 530 licensees. And that's everyone from high growth startups through semiconductor vendors and OEMs. To date, there's been around 200 billion ARM-based chips have been shipped, with around 25 billion of those in 2020 alone. So I mentioned our business model, and really, partnership is very much at the heart of what we do. So we develop technology and we license it to semiconductor companies. And for each license, we then receive a license fee. And the semiconductor partners will then go and develop SoCs and then make those shipments out to the OEMs. And for each of those chips that are shipped, ARM receives a royalty for every one of those chips that contains our technology. And so as well as collaborating with our semiconductor partners, we also collaborate with our OEM customers as well through our business development. So I'm going to look into a little bit more on how we create those chips. So making a chip can cost multiple millions of dollars. So the design's really got to be right first time. So if we take a typical design flow from an IC design house, so typically that's from requirements all the way through design, verification of the upfront design, through the implementation process, validating that implementation process, and then through tape out, fabrication, and then ultimately making a chip. So what ARM is doing is we're providing the IP that whether it's CPUs, GPUs, or systems IP is pre-validated components that our chip partners can then integrate into their designs. And because we're delivering these as pre-validated components, we spend tens or hundreds of millions of CPU hours upfront validating those designs so our partners don't need to. As well as those upfront CPUs, GPUs, and systems IP, we also provide physical IP, and these are typically the cell libraries or memory compilers that are needed to then implement and then ultimately fabricate the chip. And then similarly, what we do is spend many tens, hundreds of millions of CPU hours validating those libraries, also make sure they're correct. So why use cloud for silicon design verification? Well, as I said earlier, the tens, hundreds of millions of hours that you need. Well, cloud is really well suited for silicon design and verification. It allows us to innovate faster and collaborate better. With an on-prem compute farm, you've really got limited capacity over there, which cannot scale quickly to the needs of all the different milestones as you work through your way through your project. So what we find is when we use cloud, the ability to design, verify complex IP and SoCs, we can do that much faster, allowing us to execute projects more quickly and ultimately faster time to revenue. The on-demand scaling of resources is really important, and that allows the teams to get the compute that they need when they need it. and then the ability to work seamlessly and securely with third-party partners in a cloud-based environment really improves that collaboration. But as well as innovating faster, we also reduce risk. So what typically we're finding is when you're running multiple projects in a fixed compute farm, what you're finding is really oversubscription of compute that you need to then go and develop those products. And that really means that you lack the right hardware at the right time. So again, moving that to cloud means that you can, for those tight project deadlines, you can make the compute that you need available when you need it. We also find that as you run those projects, and then of course you're always going to find bugs, and as you want to resolve bugs and do that more quickly, you can then rapidly scale up the compute that you need, and again, it helps you hold schedule. And ultimately, this will save you millions of dollars. But we also reduce cost. So if you were to build a compute farm that meets all the different peaks that you need for running multiple projects, ultimately you're going to find that you're underutilizing those hardware resources when you are in those peak times. So moving to a cloud environment where you can rapidly scale up and scale down, that allows you to minimize your IT capital expenditure, which really allows you to maximize your resources on doing the engineering when you need to do it, ultimately resulting in a reduced total cost of ownership. So that's why cloud, but why ARM in the cloud? So we've been partnering with AWS for several years, and the AWS Graviton2 processor we've been using in production for the last couple of years. And we see some really great results with the Graviton2 processor. 7x performance improvements, 4x compute cores, faster memory versus the original Graviton. Using the 64-bit ARM Neoverse cores with the AWS designed silicon has been fantastic, and with the improved networking that's there. So what we find is as we run our EDA workloads on Graviton2 processors, we're finding a 40% better price to performance benefit compared to 5th generation x86 based instances. And they're really well suited for EDA use cases. And so we've been typically using the C6G, the M6G, the R6G, and the X2GD cores. So I mentioned our use of EDA tools. So typically, when we look at that design flow that I mentioned earlier, you can split it into your front-end design, back-end design, production test stages. And EDA tools are available on ARM for use in the cloud and also on-prem. And so we've got a selection of the different tools that are available here. And one of the ways to think about the benefit of cloud here is that you can, for the different needs of the different stages of the design flow, you can get the type of compute that you need. So sometimes you want to massively scale out using lots and lots of very cheap instances. Other times what you may need are lots of large memory machines. So you can really tailor the compute that you need to the different stages of the design flow. So we've got a few examples here across Synopsys, Cadence, Siemens, and Ansys. And there's a selection of tools that are available for all stages of the design flow. So when we look at the EDA ecosystem on ARM, and then we start to, as well as looking at the tools that are available, we then start to look at the performance. And we can see some really fantastic performance improvements versus x86. So whether it's in the front end of the EDA tools or it's in the back end, we're consistently seeing improved performance. But then once you start to then take the cost into account, so not only with the improved performance, but with the lower cost, we see some really fantastic percentage improvements per vCPU. And that's all the way from, when the 25% up to 45% or 47% improvements over there. So really great results. So I'm going to give you a few case studies. So we're going to start with physical IP design that we've more recently been running in our ARM cloud. So So with physical IP design, what we find are the workloads are very, very compute intensive. And also we find that there's a very dynamic business environment over there, which really means that having these very compute intensive workloads, and you may need to execute those workloads at very short notice, depending on the business need that you have. So that means that the scalability and elasticity of cloud fits really well. So we develop our physical IP design in ARM with our physical design group, PDG, and PDG have been running production workloads in AWS since 2019. 80% of PDG's usage on AWS is using Graviton 2 today, and so they're really taking advantage of those performance and cost benefits that I mentioned earlier using the ARM-based Graviton 2 family. So typically, again, in terms of benefits, they're using ARM in the cloud. We're able to address that peak CPU demand. But then what we also find is the increased productivity of the engineering teams through that dramatically improved turnaround time. And I've got an example I want to share with you today. So what we found when we then start to think about using cloud in this area, we're really finding that the teams they move from being CPU limited to really being human limited in terms of how they can execute their projects. So on the table on the right, so if you look at the red line, there's around 4,000 CPU slots. What we were finding was with the fixed capacity on-prem, there's only so fast that you can go. But then when you remove that restriction and then you start to run in the cloud, you can see the blue trace, which is allowing you to ramp up really, really quickly. So way beyond 4,000 slots up to 25 or even 30,000 slots. And then crucially, you can ramp that back down again. And so in the trace here, there's a couple of ramp up and ramp down stages. So just to put some numbers on it. So typically the team would be requiring around 4,000 slots over 4 months to run their project. And then by increasing the scalability, they're able to run 20,000 slots for less than a month. So with the massively improved scalability and efficiency, we see a much improved reduction in cost and runtime. So as well as the physical IP design, we also do a lot of hardware IP verification, and that's also moved into the ARM cloud. Cortex-M55 is ARM's first CPU project to move to the cloud. It's also the first to find bugs using ARM architecture servers. We started our migration to the cloud before Graviton was released, and around 30% of validation in that first pre-release phase moved to the cloud, and that contributed to a significant increase in test cycles. And so the product quality improved in those early stages while still hitting the original release schedule. Moving to Graviton 2 increased the simulation performance by nearly 20%, and over the past year, 36 million CPU hours have been spent on M55 validation in the cloud. So one of the things that makes us very happy is then when we get feedback from our engineers. So Yashay Bhattacharya is our lead validation engineer for Cortex-M55, and she was really able to get the massive benefit of using ARM Cloud with the Graviton 2 processors to really scale the verification, and that gave that much improved confidence with the additional quality that was achieved by dramatically scaling CPU cycles. So the trace on the right just gives you a bit of an example, just to illustrate that point. So the green trace is using x86 servers, and the yellow trace is using the Graviton 2 processors. And what you can see is after switching to using Graviton 2, the nightly test suite would then complete before engineers got in the next morning, which massively improved the productivity of the engineering team. So as well as hardware IP, ARM actually does a lot of software engineering. And what we found is that with the different classes of software that we develop, that presents a lot of different challenges. So we develop embedded software, tools, models. We upstream to the open source community, and of course we provide engineering infrastructure as well. So while there are many different types of software that develop, there are many common characteristics. So the teams all need a CI/CD pipeline. They're going to need to be able to stand up, adapt, and then tear down a workflow. So as they experiment with their designs, and that really allows them to optimize the flow. And what we find is that AWS's cloud really, with the diversity that's there, really matches our requirement for a platform that can support all those different requirements. So our development solutions group, so DSG, so they make compilers, models, debug software tools to support the ARM IP. And as I said earlier, the diversity of the different product types and the teams means that there isn't really one development flow. But of course, we find that the build and test speed is very much a priority for us. And being able to turn that around quickly allows us to develop our products faster, deliver to our partners, and ultimately with better quality. So we realised quite early on that we were going to need a programmable way to describe the infrastructure that we need. So infrastructure as code, being able to deploy that quickly, scalable, in a consistent way was going to be required. So we actually built our own internal multi-architecture cloud, which was successful, but also very heavily oversubscribed. So then we began to engage with AWS, and so we started to migrate some of those workloads over there. Security is inherent in everything that we do. IP is our business, so being able to protect our projects was very, very important. So we made use of the AWS landing zones and the tools that were available there. Of course, budget is important, so comparing our use of cloud to on-prem was going to be very important, so we build that into our requirements. And as I mentioned earlier, the scalability, really important. Providing the right sort of compute at the right volumes at the time the team needs it is very important, and being able to get that with zero queue time was super important. So in the end, we overachieved. It was incredible. The infrastructure we were able to make available was so fast and stable. We actually even beat our expectations on cost. And then when the Neoverse N1 based Graviton 2 ARM-based processors became available, we were also able to migrate the teams that could only use ARM architecture. So our happy, productive engineers that we made were able to then really focus on that product delivery, which was a really great result. So a final example for you is the ARM compiler for Linux. And this is our HPC compiler for supercomputers. So it's only needed on ARM architecture. And prior to engaging with AWS and using that on-prem system, we found that our average build time was 3 hours 9 minutes, and with a worst outlier of 5 hours. Moving to AWS, then typically we're getting our results in 15 minutes. So a 92% improvement over there, also with zero queue time. So this is a real game changer for the team. So to summarise with our journey to the ARM cloud, so running ARM EDA on the ARM Neoverse-based AWS Graviton 2 instances has really resulted in massive benefits to our IP delivery business. It's resulted in significant cost savings over the x86-based instances, reduced run times and improved performance, and the job's just run, no queues or resource constraints. We'll have a greatly improved workload throughput, of course, leading to these happy, highly productive engineers able to focus on product delivery. Our EDA partners and the tools ecosystem is ready today for ARM, and ARM's here to help and share our lessons learned. So with that, I'm going to hand back to Dave.
Well, thank you, Mark. We really appreciated you sharing the journey to the AWS or ARM cloud with your EDA users and sharing how the productivity increases possible using cloud have helped to create not only happier customers for ARM, but also happier engineers. So in wrapping this up, we do have a number of links here of landing pages for manufacturing and semiconductor engineering and design available on aws.amazon.com. These include case studies, reference architectures, and deeper dive materials on the topics that we've covered today. So again, I want to thank everyone for coming today. This has been a very enjoyable session. Thank you indeed to Mark and to Walker for presenting as well. So again, thank you.